All right, so I'll try and have these quizzes graded as soon as possible. I'll put the scores into Blackboard when I do. I'm not sure if it'll be by Thursday, but it'll be in there when I get it finished. Your next assignment, homework 8, that's due a week from today. So now we're starting on chapter 5 in the book, if you're following along, and I hope that you are. The textbook explains things with a different point of view, kind of a different way of understanding compared to the lecture that you get here in the classroom. So I think it's really valuable to review in the book the sections related to the lectures. And so now we're in chapter 5, which is all about the continuity equation. You've already had a taste of the continuity equation from some of the experiments we've done in the lab. Just as application and to give you some background of how we often use the continuity equation, one of the largest reservoirs in the United States is the Oahe Dam. And it's right at the border of North Dakota and South Dakota. And they've dammed the Missouri River, and it's relatively flat out here. I mean, most of the time you'll notice if you look at a map of dams in the United States, they're most often located in mountainous areas, like in the western United States or throughout the Appalachians. But there are a few low head dams where the height of the dam isn't that high, and this is an example of one of those low head dams. They still are able to generate electricity from it. But probably the primary benefit of the Oahe Dam is flood control, where managing the flow rate of water through the Missouri River upstream as far north as the northern border of South Dakota allows them to kind of control conditions downstream, where there are other locks and dams as well. So this is a really important reservoir, and you can see that the way that they describe its volume is they say it's 23 million acre feet. So think about what that may mean. Acre we usually think of as a unit of area, and feet, of course, is a unit of length. And so rather than saying how many cubic feet this reservoir is, which would just maybe be so abstract because it's going to be really, really enormous, they try and make it a little bit more something you could wrap your mind around by describing it in acre feet. And so what that would be is if the surface area of the reservoir was 23 million acres, then it would have an average depth of 1 foot. Now, of course, that's not the case. The reservoir isn't just 1 foot deep. It varies all throughout the reservoir. But this approach of describing volume in terms of acre feet is pretty common. So I wanted to mention that to you. One of the interesting things about this photo, I think, is it kind of almost looks like it's pixelated, like it's a bad photo, like a low-resolution photo. But in reality, the resolution of the photo is fine. It's just that the way agriculture works is that fields are broken up into sections, and there's a fence line and runs north-south in a lot of cases. And so it's not that this is a pixelated image. It's just different crops have been planted in different fields. And here, those circular shapes are where they have pivot agriculture, where the irrigation lines are going about a central axis there. So it's kind of interesting to fly over the country and look at these different uses of water for agricultural purposes. But the reason why I mentioned the Oahe Dam is because at the dam, the water is impounded by a big wall that I think is soil for the most part, but there is 2 ways that the water comes out of the dam and into the river. Through most of the time, water is coming through the power plant because it's at the water through this penstock spins turbines and allows them to generate electricity. But when the water level gets so high and they have to discharge more water than can be accommodated through the power plant, then there's an additional capacity to release water through these release gates. And then, not pictured here, but dams would also have an emergency spillway in case the water gets high enough that it's just going to go over the face of the dam. There's usually a certain place where they've kind of ruggedized and intentionally improved the surface of where the water would flow and spill over the surface of the dam to try and prevent scour. But what we're going to talk about today is a couple of years ago, a situation when there was lots of storms upstream of the dam, so that the watersheds were contributing a lot of runoff into the dam, and there was so much water it couldn't all come out through the power plant. Here's just a picture of the power plant if you were standing on this side, on the right side, and so looking at the power plant, looking northward towards the power plant. You can see, I mean, there's some transformers there, but not an incredible number of transformers. This really isn't a huge electrical operation. It's just maybe a value added to the flood control benefits that this reservoir provides. Back in June of 2011, there was a lot of heavy rainfall in the watersheds upstream of the dam, and the dam had to release 160,000 cubic feet per second just to keep pace with the amount of water that was coming in to the reservoir. And just to give you an idea of what is 160,000 cubic feet per second, well, one way you can think of it is, a cubic foot, about a foot long, a foot tall, and a foot deep, 160,000 of those per second. But still, who knows what that is, right? So just for comparison, probably some people here are familiar with the Gauley River, and you know that in the fall each year they have special releases from the into the Gauley River during like whitewater season. Like if you've ever been whitewater rafting, most of the time you can go onto the New River, but it's only during these special release dates that they encourage and allow rafting on the Gauley River. And so I've been on the Gauley River during whitewater season in the fall, and it seems like it's crazy, but they're only releasing 2,800 CFS. And so to put that in perspective, we're talking about 2,800 cubic feet per second for the Gauley River at peak flow in the fall, compared to 160,000 CFS. And so this is orders of magnitude larger. This is really a lot of water. The maximum capacity of flow through the power plant is only 50,000 CFS. So they were putting 50,000 CFS through the power plant and then 110 CFS through these release gates. And I should maybe zoom in the aerial view from that. You can see that there's 1, 2, 3, 4, 5, looks like 6 release gates, and they're tapered. You see how it's kind of, it comes to a point at the end, which means that the water channel is narrow and then it gets wider. We will look at some videos of that. In fact, let me bring up the first of those just to give you some perspective of how much water was being released during this discharge event. So the water is exiting with a really high velocity. It's coming out of those pipes at a velocity that we'll calculate in just a moment, is high enough that it would definitely scour a natural earth-lined channel downstream. And so they somehow have to dissipate the energy that's coming out with such velocity and get the water to slow down and have as much turbulence occur close to the dam as possible, because they would typically have a reinforced channel for some distance away from the dam, and then it just goes back to the natural channel. Next semester in hydraulic engineering, we'll talk about one of the techniques that's used to dissipate energy downstream of a dam, and that's inducing a hydraulic jump. And we may, in one of the views, get to see the hydraulic jump, but let me just start this again so you can get an idea of really how much energy there is. Obviously, the white water is a clue that it's moving very quickly and it's entraining a lot of air as it does so. So you can see it's very vigorous. There's a lot of turbulence. You maybe wouldn't want to hop in here unless you had a life jacket on. Then it'd be fine. Okay, let me skip ahead. So it gives you an idea that the water is moving quickly, and this was round the clock. They were discharging this water day after day after day because The reservoir can only hold so much, and if the water level gets too high and it spills down the face of the dam, that's a really risky scenario that can cause quite a lot of damage. So here's the last view that we'll look at on this video clip, just showing that channel where the water is going into the river downstream. All right, so there's that, and then let's also watch this other clip. Side view. Okay, so it's really moving along. A lot of energy, a lot of velocity there. Let's try and calculate what was the velocity through those gates. So what we know is that we have 50,000 going through the power plant, but that's what we weren't looking at. What we were just looking at was the spillway release gates. And I looked up some information about those spillway release gates. They're 19 feet in diameter, so enormous, much bigger than I guess it would have looked from the videos, and I guess that's because we didn't really have anything of a known size for perspective. But those spillway gates are 19 feet in diameter, and there are 6 of them. So what I'd like you to do is use the equation that I've shared with you before, that Q equals V times A, where remember V is velocity, A is cross-sectional area, and Q is flow rate. So in this case, we're working in traditional units. And so we have cubic feet per second is the flow rate. That's the units of Q. Our units of velocity are feet per second. And then the area units are going to be feet squared. So we want to find out through each of the gates what's the flow velocity. And is it in the neighborhood of what we would have expected based on the videos that we just saw? Okay, so we have to consider that the flow is being split, let's assume evenly, among the 6 spillway gates. And so 110,000 divided by 6 tells us that through each of those channels downstream of the spillway gate, it's 18,333 cubic feet per second. The cross-sectional area for each gate is 283.5 square feet, and so the velocity should be 64.5 feet per second. Just for some perspective, it's usually assumed that between 10 and 20 feet per second is at the high end of what's safe to have flowing over typical concrete. If you have more than 10 feet per second over concrete, then over time there's going to be a lot of scour, and even in the short term there could be cavitation, because high velocity, remember, causes low pressure, and if the pressure gets low enough, then it can fall below the vapor pressure of a liquid. And so that's one of the applications that we're going to see later on when we consider Bernoulli's equation, is we can use it to predict the risk of cavitation, and cavitation can further cause damage and scour to the downstream infrastructure. And so in this case, where they had 64.7 feet per second, you can guarantee that That concrete has been finished with a lot of care and attention to how smooth it is. It's likely been reinforced with an ordinary, like a much more steel reinforcement than would typically be used just for like ordinary curb and gutter work. And so it's a specialized environment. And in fact, in some dams where they have water flowing through penstocks at a really high velocity, they'll actually inject air so that the water rides on a cushion of air instead of coming in direct contact with the concrete, just to prevent scour and cavitation and damage to the concrete. So really all of Chapter 5 is applying this formula. In fact, the entirety of the second exam covers a relatively small number of equations. If you know how to use acceleration, so there's the equation for convective acceleration, that's one, Euler's equation, Bernoulli's equation, rotational flow, continuity, and then in Chapter 6 we're going to do one related to momentum. So, I mean, there's really only 7 or 8 equations that apply to the entire second exam, and all of Chapter 5 is built around Q equals VA. So let's talk about that in some more detail. When we say Q equals VA, strictly speaking, what we mean is the average cross-sectional velocity. So sometimes you'll see V with a bar across the top, and that means the average across the area of flow. Now, when you have laminar flow, it's not going to be the same velocity everywhere in the cross-section. The reality is that there's a velocity profile because of the no-slip condition, and because there's a shear stress resistance at the boundary of the water in contact with the pipe. We'll look at a cross-sectional diagram in just a moment of that, but when we talk about flow rate, volumetric flow is what's used a lot of the time, but we can also describe flow rate in terms of mass flow. And it's the same thing as volumetric flow rate, but we're also multiplying by the density of the fluid. And so that gives the units of mass flow rate, mass per time. If we take volume per time and multiply it by density, which is mass per volume. And so mass is always conserved in fluid mechanics, mass flow rate, but volumetric flow is not always conserved, because remember that some fluids, specifically gases, have the capability of being compressed as they flow from place to place. And so when we apply the continuity equation with liquids, we can keep track of the volume in and the volume out and assume that they're equal. But in cases of gases, sometimes that's not a safe assumption, and instead we have to rely on the mass flow rate. And so mass flow rate's a really important concept. And so what we can say is that m dot, the mass flow rate, is just the density times the volumetric flow rate for a certain stream. Here's what I was talking about earlier with the effective laminar flow. And you can see that this velocity profile has a bullet shaped, where the velocity is the highest at the center of the pipe and lowest going all the way down to 0 where the fluid is in contact with the pipe itself. And so the no-slip condition says that a fluid can't slip with 0 friction across a stationary surface unless it's an inviscid fluid, and those don't really exist. So the idea of the flow rate, if we know the velocity at every point in a flow field, rather than just an average across the entire cross-section. If we know the velocity at a variety of different locations in the flow field, then we could integrate the velocity over an incremental area. So you can see here in a given radius what they've done is they've said, let's have some elemental area represent a section of our flow cross-section, and we'll find out the actual velocity at that particular point. And then if we did the same thing with all of the different elements that form the face of that flow area, then we could find the flow rate by integrating the varying velocities over those incremental areas. And the same thing with mass flow rate, it's just we take that same approach and multiply it by the density of the fluid. But the truth is we rarely have an equation that readily describes the velocity profile. And so most of the time what we're doing is we're just calculating the average flow velocity. Because remember that in laminar conditions we would have a nice, even, easily describable velocity profile, but in turbulent flow, anytime the Reynolds number is beyond the range of 4,000, then we expect there to be quite a lot of variability in the velocity. And the average velocity is relatively close to the centerline velocity, but it's not always equal. So we just have to calculate maybe the average over time, or look at the flow rate relative to the area. So just to get some exposure to the idea of mass flow rate, let's consider this case of what if we have oil flowing through a pipe and we know the mass flow rate. So through that pipe, every second there's 550 kilograms of oil. So with this given information and the mass flow rate to volumetric flow rate relationship, calculate the mean velocity of flow and also the volumetric flow rate for the oil that's described here. So you'll need to take the diameter that's given and calculate an area based on that diameter. Okay, so we have the density, the diameter, and the mass flow rate. We want to find the velocity and the volumetric flow rate. So just taking care of the units here, of course, if the diameter is given in centimeters, we're going to have to convert that to meters before we calculate the cross-sectional area. The volumetric flow rate is 0.647 cubic meters per second, and that's the volumetric flow rate that we calculated from the mass flow rate. And then once we know the volumetric flow rate, we can get the velocity by dividing by the area. And so we needed to calculate that with the diameter that's given, and it's 3.3 meters per second. All right, so mass flow rate doesn't really complicate things too much more. We are already familiar with density and how to deal with that, so no problem. Let's talk about some of the theory behind what's called the control volume approach. And the control volume approach is pretty important in a lot of applications related to fluid mechanics and environmental engineering, because it's the idea that you're keeping track of mass as it moves from place to place. And the control volume approach says, let's consider that there is a channel that a fluid is flowing through. And what we're going to do is we're going to keep track of what happens in just a certain part of that channel. And so the system is the particles themselves. It's the fluid. And the mass of a system doesn't change, but the location of the system changes over time. But from the beginning of this analysis, we just identify a certain number of particles as being a part of our system. The control volume can change its location over time, it can change its position, it can rotate. So the control volume isn't necessarily fixed, but early on as we're working through problems, we'll have fixed control volumes. Just to simplify, what we'll usually do is we'll have flow going into a control volume and going out of a control volume, and then we'll try and determine if there's any net accumulation during that time. The control surfaces are just the outside surfaces that encompass a control volume. So here in this diagram, what you can see is that because the diameter is decreasing, V2 is going to be larger than V1. So the velocities are different. Inside of this enclosed space, though, we don't see any capacity for storage. And so whatever flows in to the control volume, that same amount of mass and volume is going to have to flow out of the control volume. So the control volume approach is really just like, you can think of it as accounting. It's looking at in and out and where it is over time. And so let's look at a little bit more complicated example, like what if we had some capacity for storage? In the first illustration here, it's just a pipe that's already full, so there can't be any accumulation inside of the control volume. But if we instead define our control volume as being this tank that's connected to an inflow pipe and an outflow pipe, now things are a little bit more different because there can be accumulation inside of the control volume here. The tank water level can get deeper. And so what we're going to say is our system is the dark blue liquid, and the light blue liquid isn't specifically the system that we're keeping track of at a certain time. So this is just a picture of the control volume and where the system is within the control volume at time t. And so we have a certain mass of the system that's inside the control volume. And you can see that some of our system is outside of the control volume. It's in the inflow pipe here. So this delta M in is going to be how much mass flowed in during the increment of time delta t. So this is a before and after picture. In the before, you can see some of the system was in the inflow pipe. In the after, there's some of the system in the outflow pipe. And if you look closely, you may notice that the length of the dark blue segment in the outflow pipe is longer than the length of the inflow segment here. And you'll also notice that the liquid level is lower at time t plus delta t. So during this time increment, there was flow into the control volume and there was flow out of the control volume, and the amount of mass that was stored inside the control volume decreased. So the water that comes in can either go out or it can be stored. And in this case, more went out than was coming in during the time increment delta t. So the system itself is constant, but where it's located over time changes. And the way that we generalize that is we say that the mass of the system at time t in the first instance was the mass that was in the control volume and how much of it was in the inflow pipe, whereas at the other time increment, the mass of the system is the same, but where it's located is now some of it in the control volume, some of it in the outflow pipe. So the change of mass that was inside of the control volume was the difference between the in and the out. And this is such a simple concept, but it has really important applications to be able to say that the change of mass inside of a control volume over time is the difference between the mass flow rate in and the mass flow rate out. And so, simplified, we can just say that accumulation is in minus out. So if there's more flow in to a tank than out during a certain time period, then we'll have a positive accumulation. Here, the accumulation was negative because there was more of the system flowing out than flowed in during the time delta t. The book goes into a little bit of time talking about properties that are attached to mass. And just to go over some of that terminology, extensive properties are those that are related to the mass of a system. And so these are properties that are carried with the mass itself. And so momentum is related to how much mass is in a system. Energy is, mass itself is related to system mass. But then there are some properties of a fluid that don't depend on how much fluid mass there is. So the viscosity of a fluid isn't dependent on how much of it you have, nor is the color, or if you take one of these extensive properties and describe them in terms of per unit mass, then that makes them intensive properties. So we won't go into a lot of time talking about intensive and extensive properties in Chapter 5, but in Chapter 6, when we talk about momentum, bear in mind that when we keep track of fluid momentum and we apply the control volume approach to it, we'll be assuming that a fluid's momentum is carried with the mass. So wherever the mass goes, the momentum is going as well. So its properties are transported with the fluid across a control surface and through the control volume. Okay, now back to the Oahe Dam. I have a handout for you, and what we're going to look at is its surface area and how long it would take to drain the dam if we had the area that's known, and we know the average depth of the dam, and then there are a couple of places where water is flowing in, and we have the flow out through the spillway and power plant that we talked about before. So what I'd like you to do here is apply the principles of mass flow rate, volumetric flow rate, and try and figure out how long is it going to take for this reservoir to become drained. And you can search online for any units conversions that you need. I think you maybe, if you don't already know how many square feet are in an acre, if you don't have that one memorized, then you'll need to probably Google that, because you're going to need it to solve for how long it's going to take. So here's the conceptual sketch that I came up with, and what you're going to need to know is what's the area, and then what's Q in for location 1 and 2, Q out, all in terms of cubic feet per second. So each of the streams is described a little bit differently, and what you need to do is calculate the cubic meters per second of each, and then look at accumulation is in minus out, and that'll be the key to finding out what rate is the liquid level decreasing at. Okay, we've burned through all of our available time, so let me show you the basic idea on this, and I would encourage you to take it home with you and think through the rest of it. Actually solve this example. It's an important one. We can calculate the area based on 43,560 square feet per acre, so we know the area of the reservoir. The flow rate out is defined. That's the 160,000 CFS. The flow rate in 1 is talking about the river that's 40 feet wide, 8.5 feet deep, and has a known average velocity. So from that we can get the volumetric flow rate from the river. And then that upstream dam is releasing 13 times 10 to the 6th pounds per minute. So we can convert that into cubic feet per second by dividing by the density. Then it gives us the volumetric flow rate per minute. And then dividing by the volumetric flow rate per minute by 60 gives us volumetric flow per second. So there's a little bit of water coming into this reservoir and a lot of water going out. So the difference between the two, the accumulation is negative because there's a little bit in and a lot out. So the net accumulation is negative 155,338 cubic feet per second. So that means that over time the water level is going to be getting lower and lower and lower. And so if we look at the volume of the reservoir, so that's the cross-sectional area, top view, multiplied by the average depth, that tells us how many cubic feet of water are in the reservoir. And so then the time will be the volume divided by the flow rate out. So here we've calculated the time in seconds, but what that works out to is 76.3 days. I know we worked through that solution really quickly, and probably you'll take some more time to think it and digest it. Here it is now 12:17, so I'll make sure that you get those extra 2 minutes back when we meet on Thursday. I don't want to keep you too long, so all right, I'll see you then. Okay. I'll see you during lab today.